How can we determine the velocity of an object falling in a viscous fluid? Have you ever thought of that? That concept is terminal velocity. So we define terminal velocity as what? The maximum velocity attained by a body falling in a what? Viscous fluid. So please, the important concept we should note about terminal velocity, which is denoted by Vt, maximum velocity by a body falling in what? A viscous fluid. So the first concept is the maximum velocity. The next is what? The viscous fluid. Of course, maximum velocity is the highest velocity of that object, and viscous fluid. So when we talk about viscous fluid, you should know that viscous fluid is gotten from the term viscosity in fluid. Then now you should understand the concept of viscosity. Viscosity is what? The internal resistance between the layers of a fluid. That is what viscosity is. So everything we're talking about is what? The maximum velocity or maximum speed attained by an object falling in a fluid that has internal resistance. Now let's illustrate this with a diagram. Now let's pick a cylinder object, or let's say we have this as the object, and let's say this is the body, and of course the body should have a weight, which is the weight of an object. In this case, let that object be a sphere, more like a ball. So take note. So this is the object, it must have a weight, and since it's falling in a viscous fluid, there must be what? A buoyancy, or what? An upthrust. Of course, upthrust is always present when a body is falling in a fluid, and it acts opposite, right? So it acts in an opposite direction. So we donate the upthrust and the buoyancy. Let's call this FB. And there's another thing we should know, known as the drag force. Drag force is what? Is a force that is present in what? In fluid, and it acts in opposite direction. Now take note, that drag force will be known as what? The viscous force. So you should know another concept. Drag force is the viscous force. Of course, let's donate this by FV, and let's donate the buoyant force, which is the same thing as the upthrust, as what? FB. So these are the concepts you note. So of course it acts in an opposite direction to what? The weight of an object. So we're having it up, FV. So please, we have the weight, we have the viscous force, which is the drag force, and we have the buoyant force, which is also the upthrust. Now, I've told you earlier, these are the systems of the forces you have in, of course, a viscous fluid. Now, but to determine what? The velocity. You should note that the object falls with what? Velocity and what? Gravity, acceleration due to gravity. It also falls with what? An acceleration of that object, which is A. It falls with A, you should know. So understand those concepts. Gravity acts on the fluid. The ball is accelerating too. So take note, V, of course, the body has a velocity which is known as the terminal velocity. So please, the concept is very easy. Now, we are going to use the principle of equilibrium of forces, which is the sum of the forces in the left hand side must be equal to what? The sum of the forces in what? The right hand side. Using that principle of summation of forces, you notice that it is also known as the sum of forces in what? In the downward direction, or let's say upward force, is equal to what? Sum of forces in what? Downward force. So those are the concepts. Very important concept. Now if we look here, we have the upward force, which is Fv plus what? Fw, the viscous force plus what? the buoyant force equal to what? The weight is the only force acting in what? In the downward direction. Now, what we're going to do is we're going to make the buoyant force subject formula. So it becomes FB is equal to what? The weight minus what? The viscous force. The weight minus the viscous force. But you must notice that what? The buoyant force and the weight can be expressed in terms of mg because they are forces. So of course, the buoyant force FB can be expressed as mg, and the weight of an object can be expressed as what? Mg. So please take note, this is what? The buoyant force. This is what? The weight. Now let's put a prime here in the weight so that you should know that the buoyant force is equal to the weight of the fluid displaced. So it's a very important concept. You must know that what? FB is what? Equal to the weight of the fluid displaced. Of course, very important concept. And that weight of the fluid displaced can be expressed as in terms mg, but we should know that what? Mass is density multiplied by what? Volume. From the concept that density is mass over volume, right? So of course, if you substitute that value, you have the what? FB is equal to what? Rho v g for the buoyant force. So now, of course, we said that the buoyant force m it has prime right on the m. So we're going to bring that prime here. That prime will be attached to what? The density. Take note. And if you know that what? Take note that also the weight is also mg. And we said that what? The mass is the density multiplied by the volume. So you have rho v g as, of course, the formula for what? In terms of what? Density and volume for the weight of the object. In this case, the object is sphere. Now you should know about some concepts. Now we have for the buoyant force rho prime vg. For the weight we have what? Rho vg. Now you should know that the density prime is of course for the buoyant force. So it's going to talk about what? The density of what? The fluid, which is the fluid. And the one that don't have anything, which is normal density as a result of the weight, is the density of what? The object. So those are important concepts. The one that has rho is the density of the fluid. The one that has this is the density of the. Now, of course, we're going to substitute those values into what? Into our equation. For now, let's look at this. Let's make the viscous force the subject formula. Let's make the viscous force the subject formula. So you have the viscous force is equal to the weight minus what? FB. So it's very important we leave it this way because we're trying to substitute what the weight and the buoyant force is. That's why we're expressing them in terms of the density and what? The volume. So please, the viscous force was to be made for subject formula here in this case. So of course, we're going to substitute that value. So we know that what? FV, which is the viscous force, is what? The weight, which is in turn, the weight is what? Rho Vg negative what? For the buoyant force is what? Rho prime Vg. So we have rho prime Vg. Of course, from this concept now, you notice what? The volumes and the gravity acceleration due to gravity are equal. So therefore, we're going to factor that out. So we have a case where we're having the volume, gravity, rho minus what? Rho prime. Of course, when we have reached this point, we will notice that we're considering the volume of what? A sphere, right? We're considering the volume of a sphere. Of course, we know that volume of a sphere is equal to what? 4 over 3 pi r rho cube. Of course, this is a ball or a sphere. A sphere has a radius r, right? So that's the concept. A sphere has a radius r. So if we substitute that value into what we have here, we see that the FV is equal to what? So we have 4 over what? 3 pi r rho cube g into what? Rho minus rho prime. So please, when you have reached this point, we're now going to take the concept of what? The viscous force. So you should know that from Stokes' law, we have an expression for what? The viscous force. So please, if you don't understand the concept of Stokes' law, you can do your research. But I'm just going to take that formula out. It's very important to cram the formula for Stokes' law. Now, from Stokes' law is an assumption which is gotten by using assumption of dimension analysis to verify if that law was correct. And I remember from Stokes' law, which is in this case, we have a case where it's given as 6 the terminal velocity multiplied by rho pi and what? The coefficient of viscosity. So you should take note that rho is the radius, Vt is the terminal velocity. Of course, everybody knows that terminal velocity. Then this is called what? This is called coefficient of viscosity. So please, important concept is what? Rho Vt, which is the terminal velocity. Let me write it down. Terminal velocity. Then this is called what? Coefficient of viscosity. Of course, this is pi and this is 6. So those are the remaining concepts. So we're going to substitute this value of what? Stokes' law. This value of Stokes' law into what? What we have here. So please, of course, this is the equation we're working with now. So if you substitute that value, you have what? 6 Vt rho pi, of course, coefficient of viscosity is equal to what? 4/3 what? Pi rho cube g bracket what? Rho minus what? Rho prime. So please substitute those values. What did you notice? Rho here will cancel one arrow here, 2 will be left, right? The pi will cancel this pi here, and you notice that 2 will go into this, you have 3, 2 will go into this, you have 2. So when you're writing this, you write this as what? This becomes 3 Vt. Of course, you're left with what? Only what? The coefficient of viscosity. You're left with 2/3 rho square g bracket what? Rho minus rho prime. Of course, at this point, we'll work on this. I'm going to make Vt subject formula, which is the terminal velocity. Please, now we're going to make Vt subject formula. But before we do that, let's move what we have here to the other part of the board. So when you do that, you have that 3 Vt, of course, coefficient of viscosity is equal to what? 2/3 rho square g rho minus rho prime. Of course, we're going to make Vt subject formula. For us to make Vt subject formula, we're going to divide both sides by what? 3 rho over what? 3 rho. That is how we make Vt subject formula. Of course, this will cancel this and this will cancel this. You're left with Vt. Of course, you're having 2/3 rho square g bracket rho minus what? Rho prime over what? 3 coefficient of viscosity. Of course, when we work on this using the principle of Farad, nearer the nearer, let me explain that concept. In a case where you have 2/3 divided by 3, now you put over 1 here and you invoke the law of Farad, nearer the nearer, which states that the two nearer components will multiply each other and the two far components will multiply each other. So in this case, it becomes 2 multiplied by 1/3 multiplied by 3. It's 2/9. So we're going to use that law of Farad, nearer here. It becomes Vt is equal to what? 2/9, because you're having over 1 here. This 3 coefficient of viscosity will multiply 3. So it becomes 2/9. Of course, you understand what I mean, right? It becomes 2/9 coefficient of viscosity rho square g bracket what? Rho minus what? Rho prime. Of course, this is the time to write the given parameters. Of course, you should know that Vt is what? Terminal velocity. Terminal velocity. You should know that this symbol here is called coefficient of viscosity. I'm going to write it again. Of course, that's what we have here. Then we know that r is what? The radius of what? The ball or object. Then, of course, g is acceleration due to gravity. So g is what? Acceleration due to gravity. Then what do we have here again? Of course, rho is what? The density of what? Of the object. And rho prime is what? The density of what? The fluid. So this is 2 over 3 coefficient of viscosity r square g bracket rho minus rho prime. So please, this is what? The formula for what? Terminal velocity. Now let's solve some sample problems, of course.